Hi, welcome to the Unit 1 Notes over Matter. So in this unit, a very consistent thing that we're going to see over and over again is the relationship between solid, liquid, and gas, and how the particles are changing behavior to move between those states, the solid, the liquid, and the gas states. So, let's look at the different types of motion, shape, and volume of each of these states of matter. So with a solid, the motion is slow. It's almost like a vibration. The shape is fixed, and the volume is fixed. Now, when I talk about this motion here, it's kind of illustrated in this picture. You can see that there's like these little nudge marks that kind of show that it's kind of going back and forth like this and just kind of slowly vibrating. The huge misconception is that like the particles in a solid, because when I look at this tissue box, I can't see particles moving, but when I look at a liquid, I can see that moving. The particles have to be moving, but why can't I see something moving here? Because these are moving so slow that you can't tell that they are. But they're still moving. Everything's moving. Okay? The shape, just like we see here, is fixed. The volume is fixed. That's solids. Let's look at liquids. The motion is, well, I don't know about you, but looking at this liquid versus this solid, liquids move faster than solids. Okay, think of it almost like if you get like a pit of snakes, just a bunch of snakes in a pit, and you see them like kind of going all over each other. That's kind of what the particles in a liquid are doing. They're just kind of like a flowing around each other. They're not moving like really fast, but enough to where they can kind of move around each other and be pretty malleable. Okay, the shape is not fixed. When I move it around this bottle, the shape of the liquid is changing, but the volume, the amount that I have of the liquid is not. So even though the shape of liquids can change, the volume is fixed. So the shape is not fixed, but the volume is fixed. Okay, you can see that illustrated here. That kind of like, I guess, movement symbol is bigger than in solids. And then we get to gases, and you can obviously see that the motion of gases is the fastest among our three examples here of solid, liquids, and gases. Gases are the fastest type of particle. The shape, gases. They don't have a fixed shape. They're gonna fill up a balloon, or as soon as you go with the balloon and you make that annoying like sound, they'll fill a room up. So they don't have a fixed shape. So it's not fixed. And then the volume is the same. The volume of a gas is not fixed. Okay, and just to I guess give you as good of an example as possible, if you think blowing up a balloon, you sit here and you go to a balloon, it expands, okay, and then whenever you have like, let's say you have 100 gas particles in there when you into the balloon, and then you let the balloon out, those gas particles now fill up the room. They've expanded. They don't have a set volume. Let's go to the next slide. Okay, so how do we get from solid to liquid, liquid to gas, and then back down from gas to liquid, liquid to solid? if we're looking, let me grab this. Okay, so to get from liquid to solid, we know that's freezing. Okay, and we know to get from solid to liquid, that's called melting. But at what point does that occur? We call that moment at which it occurs the freezing melting point. And if we're talking about hey, what's the actual number that happens at? That's at 0 degrees Celsius. At 0 degrees Celsius, liquids will freeze if they're held at that temperature. And if solids are held there and then barely taken over 0 degrees Celsius, they'll start melting. Okay, fair enough. Pretty straightforward. Okay, so what if we heat something up at 100 degrees Celsius? Well, liquids will start to boil or, liquids will start to boil or vaporize. Another way to say vaporize is evaporation. I don't know about you, but I think Star Trek, vaporizers, that's just evaporating something really quickly. They mean the same thing. And then if you have a gas and you cool it under, if it gets to 100 degrees Celsius, then it goes to 99.9 degrees Celsius, condensation will start. That's whenever you're outside and it's really hot and then you go back inside or you put something in your car or whatever, that's that dew, that wet stuff, the water that forms on the outside of the bottle, that's condensation. That's all that is you bring something from being really cold outside or outside to being cold. That's when the condensation occurs. Okay, what is a physical property? A physical property is an aspect of matter that can be observed or measured without changing it to a different substance. So, physical property, the thing is still continuing to have the same identity. That's the big thing. Okay? Chemical properties, on the other hand, are those that can only be determined by trying to change something's identity, some type of substance. Set it on fire, blow it up, make it rust. You're really doing a number on this thing. Okay? So you have to try to get them to have a chemical reaction, i.e., something blowing up, catching on fire, making something toxic, to determine if that property exists. Think Mythbuster reactions. So let's look at a couple. Let's look. Is melting point a chemical or physical property? Well, with a chemical property, it says we have to change them into something else. With physical property, it can be observed and the thing still remains the same. So, can I observe melting point without changing the substance? Well, if I melt a block of ice, well, that's water, right? That's frozen. And if I change it to a liquid form, it's still water. So melting point would be a physical property because the thing is still staying the same. It's still water. What about mass? If I change the mass of something, it's still going to be the same thing. So that's going to be a physical property. Density, same thing. It doesn't matter how much water I have. I could have this little bottle of water, or I could have a whole swimming pool of water. The density of each individual droplet is going to be the same. Look at flammability. How do you test flammability? You set something on fire. That's going to change what it is. That's a chemical property. Chemical stability. How do you test if something's stable? You blow it up. You mix it in a reaction and then something happens and it changes what it fundamentally is. Same thing with reactivity. To see if something's going to react, you got to test it to see if it blows up, to see if it rusts. Toxicity kind of falls on the same point. How do you know if something's going to be toxic? You got to drink it, eat it, see how it... you have to test it on a skin sample to see if it starts creating a reaction. Let's look at color. Color. That's one that kids will kind of battle on there. Where does color fall? Well, let's look at this one first. Let's look at solubility. Solubility. All that term means is the ability for something to dissolve. So to go from a particle size this big to that big. So solubility would be physical, okay? Because you're not changing what it is, you're just changing how much and the size of the thing, okay? So let's look back at color now. So the color of something, is that a chemical property or a physical property? It's going to be a physical property, the color. Now, a lot of people will say, well, if you burn something, that changes the color, stuff like that. But we're looking at it as in a sense of change. So when we look at color, that's a physical property. You can observe it without changing the substance. You can observe color. Hardness, physical. You can observe how hard something is. You can chip part of it away, and the substance is still what it was. Luster, same thing. Okay, you can observe how shiny something is. You can scratch off some of it, okay, and it's still the same material. It's whenever we have to blow something up or make something react with something or check to see if it's stable or set it on fire that it's a chemical property. Two types of physical properties. We have intensive, which are physical properties that remain the same, even if the sample size changes. They are part of the substance's identity. And then we also have extensive physical properties, which will change with the sample size. Okay? So, doesn't matter how much I have of something, it'll always have the same color. Mass changes. Temperature, if I go stand outside, I'm going to be the same temperature as the person next to me if we're all standing outside at the same time. And if you don't think about regulation of body temperature, stuff like that, and they could be twice my size. Temperature doesn't matter with size. Density, okay, same thing with the water example. I could have this much water, or I could have a whole swimming pool. Each individual droplet will have the same density. Luster, boiling point, I can have a bunch or a little, it's all going to boil at the same boiling point. Same thing with melting point. Malleability. Now some people can make the argument that, hey, if you have a big piece of something, it'll be easier to bend. And that logic, kind of makes some sense, but malleability is an intensive property because it doesn't matter how much you have of something, it'll have the same properties that allow you to bend it and to turn it into something else. Okay, it just gets easier for us when there's more of it because we have to think of like lever arms, and that's physics, don't worry about that. Volume. Volume is definitely one of those extensive ones. Odor. Now some people would say, okay, you can make the argument for intensive because, something's smelling a certain way, it'll always smell that way, like have the same odor. But then you can think like, okay, so think of one rotten egg versus 20,000 rotten eggs. The odor is going to be way worse, there's going to be more of it. So we're not talking necessarily about the extent of odor, but the quality of odor, and that the per unit amount of odor would make it intensive. And conductivity. Doesn't matter how many magnets you have. If you look at like an individual part of a magnet, if you have a little one or a big one, you take that little part, they're going to have the same conductivity, the same ability to attract metals, the same ability to attract electricities, all that jazz. Okay, something is a physical change if 1, the intensive physical and or chemical properties remain the same. 2, The change can be reversed using physical methods. Some examples. Got a good example. Chopping. Burrito. Chopping wood. Okay. I cut a log in half. Still wood. Tearing paper. Okay. I tear a piece of paper. Afterwards, still paper. One more example. Breaking glass. Okay. I'm not going to shatter anything. If I shatter a glass vase, okay, yeah, there's a million pieces, but I can still technically put that vase back together. I'm probably a little too lazy to do that though. Okay, let's look at chemical changes. Okay, chemical change occurs whenever the intensive physical and or chemical properties have changed. Can only be reversed with a chemical reaction. So examples. When I think of chemical reactions, I think of stuff blowing up. Boom. I think of stuff that is burning or on fire. I think of anything that's rusting. Okay, those are irreversible processes. Now you may say, oh, you can, do this sand spray for rusting. You're actually just getting rid of the rust. You're not necessarily like replenishing the surface and like reversing the process. You're just getting rid of that layer because it's rusted. Also, like the reactivity of something like spontaneously combusts, or something tarnishes, which is basically like a fancy way of saying rusting, but for like silver and copper. Okay. Tire inflated with air. That's going to be physical. Cake baking, chemical. I'm going to give you a sec. Please pause the video and fill out the rest. Okay. Ice melting, physical. Food being digested, chemical. Rusting iron, chemical. Grass growing, that is chemical. Water absorbed by paper towel. Water is still water. Paper towel is still paper towel. Pancakes cooking. Anytime you see something like cooking, rusting, fire, that's all chemical. Piece of wood chopped, physical. Water boiling, physical. You're boiling it. You're changing it from a liquid to a gas, but it's still water. This blah, 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 decomposing to something else. It's changed what it is. That's chemical all day long. Sugar dissolving in water. Remember, solubility, the word dissolving just means the particle size is going from this to this, which means it's still staying the same. So sugar dissolving in water would be a physical change. Okay, evidence that a chemical change may have occurred. Change of odor, change of color. Sometimes, remember I was talking about like food dyes and stuff like that? Like I added this Mio stuff to this drink right here. That wasn't a chemical change. I was just adding stuff in here and then it dissolved. And we know that if something dissolved, that's not a chemical change. That's a physical change. It just goes from a particle size this big to itty bitty. I'm actually going to take a drink real quick. Oh, that's strong. I had to make it like a dark color so y'all could see it, but that is terrible. Yeah, blueberries. A change in temperature. Okay, so if something heats up or gets really cold, a chemical reaction has happened. Change of composition. After something burns and leaves ash, or after something explodes, you get like a weird smell, and there's like bubbles and gases, or there's like ash left behind. If you see a big light or heat given off, that's definitely a chemical change. Formation of gases and bubbles. Now you may think, hey, if something's boiling, that's going to form bubbles. That's a physical change, though, when something boils, okay, when you introduce heat. But if you have a reaction going and there's not like any kind of Bunsen burner or anything, it's just a glass and you mix two things at room temperature and then it gets hot, chemical. If you introduce heat to make something boil, physical. Formation of a precipitate. We'll talk about that. That just means like some like growthy kind of solid forming at the bottom of a mixture, and you're like, ugh. Okay, the change is difficult or impossible to reverse. When you set something on fire, it's kind of hard to get it back. Okay, let's talk about last couple things here. Qualitative data. So when I think of qualitative, I think quality. What's going on? Give me data that's being observed, not necessarily measured. So when you think qualitative, you're not thinking of numbers. You're thinking of kind of what you see on the screen right now, which is your five senses. What am I seeing? What am I hearing? What am I smelling? What am I tasting? You're not going to do a lot of that this year. That'd be bad. And what am I feeling? Okay, so when something burns, I can smell it. I can see the embers coming off of it. I can see the gas. I can hear the crackling while something's burning. I can almost taste the ash and that fiery kind of charcoaly wood taste in my mouth. I can feel the heat radiating off of it. Everything I just listed was qualitative description. On the other hand, we have quantitative. Okay, I burned 506 grams of wood. Okay. It took 20 minutes to burn. It's very numbers based with units. You're describing, hey, how long did it take? Oh, I used this much. And that's where we'll stop. Okay. The next video we'll talk about physical separation methods. If you have any questions, please reach out to your teacher via Remind or through email. Have a good one.